This is my first video in my module on complex numbers, and in this one we're going to just explain a rationale for the imaginary unit I in the first place, and then just talk about how to rewrite expressions with respect to I, or in terms of I. So let's go ahead and consider this problem that I've got right here. If somebody said to us, divide 10 into two parts, some x and some y, split it up like 4 and 6, or 5 and 2, or 1 and, or sorry, not 4 and 6, 5 and 5, or 1 and 9, something like that. But when we multiply those, we get 40. You might go ahead and start by saying this. Well, two numbers that add up to be 10 that multiply out to be 40. I can't think of any. 1 times 10, or 1 times 9, which 1 plus 9 adds up to be 10, but doesn't multiply out to be 40. You can say like 2 plus 8. They add up to be 10. They wouldn't multiply out to be 40. This doesn't exist. Okay, so it's an impossible problem. But we can actually solve this. So what it does is it presents a system of equations where we say, look, the two numbers add up to be 10. And they multiply out to be 40. And we can actually solve this using the substitution method. So the substitution method, recall from algebra, says we'll just go ahead and pick a variable to isolate in one equation. We'll throw it into the other equation. So we end up with this. What if we were to, say, isolate y in this first equation? That is, get y by itself. We take the x, we put it over here on the right-hand side, and we produce this second equation, or third equation rather, where we get this is 10 minus x. So in the second equation now, we'll go ahead and plug this in where we see a y. And it produces this other equation down here. We say x times the quantity 10 minus x, which really represents the same thing as y, is equal to 40. So in order to solve this, I'll go ahead and distribute this. We get 10x minus x squared equals 40. And if you remember from algebra, the way we are going to use to solve this would be set it equal to 0. We could attempt to factor it. Of course, and that's not going to work for us here. Actually, I'm going to multiply everything by a -1, which won't affect this 0 on the right here. It will switch everybody's signs over, but essentially, it's like trying to answer the same question we were trying to do before. If I tried to factor this, really, I'm saying two numbers that multiply out to be 40 add up to be, in this case, -10, because I switched the signs, but it's not possible. So what we'll do is we'll run the quadratic formula on this. Since it is in standard form, so we have our a value here, our b value here, and our c value here. We can recognize that a is 1, b is -10, and c is 40. Let's go ahead and use the quadratic formula that says, well, the answer to anything in standard form, set equal to 0, would be this for your x values, b squared minus 4ac all over 2 times a. So in this instance, we kind of get this. We say negative b, where b is -10, so we say -10. Oops, let's do this. Plus or minus the square root of b squared minus 4 times a times c all over 2a. We'll fill in the blanks now. So we have a b here and a b here, -10. A is 1 and c is 40. We also have an a down here. This simplifies down into this expression where we get -10 in front, so positive 10, plus or minus the radical of all of this all over 2 times 1, which is 2. But when you square your -10 here, you get 100. I notice that I'm taking a negative times a positive, so this all comes out to be negative, and 4 times 1 times 40 is 160. So essentially what we see here is this. We get two solutions, but the solutions happen to be this. 10 plus or minus the square root of -60 over 2, which isn't very helpful here given the fact that I have a negative inside my radical. So this gives birth to the idea of imaginary numbers, and essentially it does so because what you see is this. There is no number that I could take times itself and get a negative product. So that would be like, if I took a positive times itself, I'd get a positive times a positive that produces a positive, and if I took a negative times itself, I get a negative times a negative, which gives me a positive. So what we need to do is we need to come up with a number that would allow us to, evaluate the square root of -60. And so that number we come up with is I, okay? We say I, by definition, is equal to the square root of -1, okay? And the reason why we define I is because it has the unique property that if I is equal to the square root of -1, then if we were to square both sides of this expression, we would end up with this. I squared is equal to -1. So I has the unique characteristic that it is the only number on the planet that when you square it, you get a negative result, okay? So the reason why this is beneficial here, we can take a trip up here in the top right. We say the number I is such that I squared equals -1. It's the only number that when you square it, you get a negative result. We could say I is a number whose square root is -1. The reason why that's beneficial is because we could have rewritten the square root of -60 as this. We could have called the square root of -60, square root of -60, as the same thing as plus or minus I out front times the square root of +60. And let me tell you why. We know that if I is not a real number, it's an imaginary number, then we can use the number of I to write square roots of negative numbers without a negative sign. So in our reasoning here, again, if we were to take the square root of a negative number, which we don't have an answer for, it's not a real number, we could say this is the same thing as the square root of I squared, because when I square an I get a negative 1. In other words, this is the same thing as a times negative 1. We know that's the same thing as a times, well, negative 1 equals I squared. And the square root of anything squared is just itself. So the square root of this 2 squared right here, or this I squared, excuse me, would be just I, and then we leave behind the a on the inside. So, going from point A to point C here without skipping through the middle reasoning essentially says this: if you have the square root of a negative, you are allowed to just throw an I out front and call what is on the inside positive, okay? So that being said, let's go ahead and take a trip and visit a few of these right here. Learn how to rewrite the square root of a negative in terms of I, and then we'll go on to our next video, which involves complex numbers. So we want to write the following radicals of negatives in terms of the imaginary unit I. We simply know this: the square root of negative 16, okay, that'd be the same thing as, say, the square root of negative 16 times, need to go back and fix this here. We say that'd be the same thing as negative 1 times the positive 16 in here. And that's the same thing because of the properties of radicals as the square root of negative 1 times the square root of positive 16, since we can split this up here. If you multiply two radicals, you can multiply the stuff on the inside. But we know that the square root of negative 1 by definition is I, and this times the square root of positive 16. So essentially, we could just do this: take the original statement, put an I out front, call what's on the inside positive. And by the way, the square root of 16 is plus or minus 4, so we get plus or minus 4I in this instance here. Okay, rewriting the second one here, using the quick route, it just basically what we've been saying is this: we say the square root of negative 20, we could rewrite this as an I out front times the square root of positive 20, and then just reduce this as we normally would, which would mean we'd say, well, this is the same thing as I times the square root of 4 times 5, and the square root of 4, of course, is plus or minus 2, so we get plus or minus 2I times the square root of positive 5, and this would be rewriting it in terms of I. And then last but not least, if we had like a prime number in here, it doesn't matter. We could say, well, the square root of 13, negative 13, is the same thing as put an I out front times the square root of positive 13. And we write plus or minus because of a technicality. Okay, so a few really quick things I want to mention before we end this video. But first of all, this is extremely important to write radicals of negative values in terms of the imaginary unit I when applicable before using the properties of radicals. So I give a correct and an incorrect example of what I mean here. If somebody were to ask you to take the square root of negative 4 times the square root of negative 9, well, first of all, we recognize that you can't take the square root of a negative. So what we'll do is we'll make these inside radicand quantities positive again by putting i's out front. So we get this: we get I times the square root of 4 times I times the square root of 9. Well, we know the square root of 4 to be 2 and the square root of 9 to be 3, so we get 2 times I for this first expression here, and we get 3 times I for the second one. So now if we were to multiply these out, we get 2 times 3 is 6, and I times I, we'll just treat it like we do with x's. If you had x times x is x squared, well, I times I is I squared. And the thing with I squared is we need to recognize this and memorize it. Memorize it today, right now. I squared is negative 1. So wherever you see an I squared, we can go plug in a negative 1. So we get the same thing as 6 times negative 1, which gives us this negative 6 right here. So what I mean, the incorrect way of doing this would be like not taking the i's out front first. You always need to rewrite this negative radical thing, or at least a radical of a negative, in terms of I first, like we just did, because if you don't, you may run the risk of taking square root of negative 4 times square root of negative 9 and getting the square root of negative 4 times negative 9, which would produce a positive 36 in here, which only gives you 6. But in this case, we want the negative 6, okay? So I say the properties of radicals that we learned in algebra only apply to expressions in which the numbers under the radical sign are non-negative, okay? So when we use properties like the square root times the square root, you can just multiply the stuff on the inside and make one giant square root. That only works with things where the stuff on the inside is not negative. So if you ever have a negative on the inside of a radical, your first job is to do this: rewrite it in terms of I. That is, put an I out front, then make what's on the inside positive, then work with your stuff. Cool.